thing that one has to think about. Not only just writing out these numbers, then they get printed.
You're getting carried away about logarithms.
Yeah.
I mean, you can easily get carried away from it, or you can easily look at the logarithms and think, right, never mind what you think when you. Anyway, and look, where does E crop up?
So E crops up because, as I've said, that the Naperian logarithms were to the base E, which means that if you raise E to the power of a number, then that is the logarithm of that number. So e to the power 2, for example, equals something.
Did Briggs and Napier know about E?
No.
So what were they? Well, you're calling it E.
Yes.
What did they call it?
They didn't call it E.
So what did they call it?
I don't know actually. So it didn't. Although it actually appears for the first time. There's a table of logarithms that are produced in a couple of years after Napier, which are tables of logarithms to base E. But again, it doesn't appear as a name. So the first time it's actually named is in about 1668, I think, in a publication then, and it actually appears.
Right, well, let's go on with this journey towards E and call out when Google again. One of the most important uses of E is in a branch of mathematics called calculus. So can we talk briefly, we've already talked about Newton and Leibniz and calculus, never mind. Rates of change, calculus, very important for cannonballs and planets and everything else, right? Where does E crop up?
Okay, so yes, calculus is the maths of rates of change and of their opposite of rates of change, which is accumulation. So for example, my rate of change of distance is my speed, my rate of change of speed is my acceleration, and conversely, my accumulation of acceleration is my speed, and my accumulation of my speed is the distance that I've travelled. So that's what calculus is about. On the one hand, rates of change, and on the other hand, accumulation. The way in which E first appears in this context, or the way in which we now think of E as appearing in this context, it wasn't quite seen as that initially, is that we've been talking lots about E to the power this and E to the power that. So slowly there was appearing the idea of a function called E to the x. And what that means is I pick a value of x and then I multiply E by itself that many times, and that's what E to the x is.
X could be 11.
X could be 11, and the answer then would be E to the 11, which is a horrible messy number, but anyway. Now, the magic thing about E to the x is if I look at what that function's doing at any point, its value is the same as its rate of change at that point. So if I look...
Can you just say that again?
Absolutely.
Yeah.
So if I look at, say, E to the naught is 1, if I look at the slope of the curve of E to the x at the value naught, then it's going up 1 for every one that it's going along.
Right.
E to the 1 is E. If I look at the slope of the curve at 1, it's going up E for every one that it's going along. So it's a magic value, E, in that it's equal to its own rate of change when I look at the function E to the x.
Now we have Leibniz and Newton they did dispute who was the true originator of calculus. We'll have to leave that to one side. Leibniz was beguiled by infinite numbers, Newton was beguiled by everything. Where were they? How did they take calculus to get towards E?
The way in which they took calculus to get towards E was they properly understood the way in which calculus could be applied to infinite sums. So they weren't working with E to the x the way I just explained it to you. They were working with E to the x as a big, complicated infinite sum, which I'm hoping somebody's going to get right for this show in a minute. And what they started realising was that if you wanted to find the slope of these infinite sums, then they could do so by working term by term. So each term looked something like a little quadratic, say x squared on 2, and they knew how to find the slope of x squared on 2. So what they brought in was the ability to find these slopes of things that look complicated, like E to the x.
I'm going to go to a bit of the other. What's fascinating with these are, it's curiosity, isn't it? Curiosity for the sake of curiosity. It's like ask for the sake of maths. It's maths for the sake of maths. They aren't saying this is going to make the next or tell us what population growth. They're just going and doing it. Let's continue with our calculus. There's two main operations there, integration and differentiation. Right.
Yes. Okay, so how have I got the job of explaining differentiation and integration in 2 minutes flat? Well, Cover's set this up. So differentiation is about finding rates of change. So that's thinking about my train journey coming to do this program today, thinking about finding my speed. So if I know how far I've travelled and I know the time it took, how far, what was my speed, I can find my average speed, but what I really want is my speed at a particular time. So I travelled about 60 miles in about an hour, so my average speed was about 60 miles an hour, but I wasn't doing 60 miles an hour the whole time. I got on the train, it wasn't moving for a start, then it speeded up. Went faster than 60 miles an hour for a bit, slowed down for the station and so on. So this bit's about finding rates of change, finding the speed at this moment. So I can find the average speed over the course of an hour, or I can find the average speed of 5 minutes. I could think, well, in this 5-minute section of my journey, how far have I travelled? And then do that distance divided by 5 minutes, find my average speed for that. I could keep doing that in shorter and shorter sections of time. What I really want to find my speed right now is to do that in a sort of infinitely short period of time, whatever that might mean. Or whatever that might mean is where Newton and Leibniz came in, is making sense of that rather difficult, rather subtle notion. So they were building on work of others, but they were able to kind of pin down what that was. So in terms of a graph, that's finding the slope of the graph, the gradient of the graph at a particular point. So if I've got a straight line, it's easy to find the gradient, that's how far I've gone up, divided by how far I've gone across. If I've got a curve, it's a little bit more subtle. That's where differentiation comes in. Then integration is kind of the reverse of that. So this is a phenomenon that crops up all over mathematics. So you have a process that you use in one direction, and then you ask, can I undo that process? And actually, I suspect we're going to touch on this in the context of natural logarithms and the exponential functions, because they're related to each other. So integration is the process of undoing differentiation. It's if instead of telling you the distance at each time and asking you the speed, that would be where differentiation comes in. If instead I tell you my speed at each point and say, can you tell how far I've travelled, that would be where integration comes in. That's a rather brief introduction to quite subtle ideas.
Thank you have to concentrate on it. I mean, but it's very clear. Okay, June, I agree. So the number E turns out of particular significance in calculus. Did Leibniz even feel that there was this? No, your head shaking. Right. What's the particular function of E in calculus?
Well, I mean, I think as Culver has already explained, really, it's the fact that when you differentiate it, you get the same function back again. So e to the x is differentiated, exponential function differentiated is itself again. And of course, and it's not just e to the x, any exponential function, so a natural, because e is just a number. And so any number, say like a to the x, if you differentiate that, you get itself back again times a constant. So this number e raised to the power x, and you get it back, again and differentiate it, means that it tells us about rates of change that are proportional. So that the rate of change is of e to the x you get a proportion. And this is very important in particular some of the things that Vicky has mentioned, that particularly in things like population control.
And as we call them here, there's a lot of exponentials in what's going on. I'm not asking you to simplify it.
No, but one of the early ways that E actually appears in calculus wasn't as e to the x, it was as the opposite, as Vicky just mentioned. It was as the natural logarithm. So people had been interested in integration. The natural logarithm.
So therefore it's differentiating from another sort of logarithm.
The natural logarithm means what number do I need to raise e to get the number I'm thinking of. So the natural log of 2 is the power that I have to raise e to get 2. So that's 0.69-ish. And the way in which this pops up in calculus is that people were interested in the areas under curves. This goes back to pre-calculus and Fermat. And they knew how to find the area under various curves like x squared and x and all these other different powers of x. But x to the minus 1 had been left as this unsolvable problem. Nobody could work out what the area was under the curve. equals 1 over x. So if you picture it, it shoots up to infinity at x equals 0, so we're not allowed to divide by naught, and then it slowly comes down and disappears off to naught as x goes up to infinity. So we want to find the area of the curve from x equals 1 to some arbitrary point. And what was slowly realised was that the area under that curve is described by the natural logarithm function. People took a while to realise that it was log to the base c. What they had was one of these infinite series expansions describing the area under the curve. Sometime after the fact, they realised that infinite series expansion was in fact the natural log.
Before we come to Euler and the E in plain view, can you tell us where we might encounter the exponential function in the real world? Well, I mean, mathematical world. It used to be mathematical real world, in the shadow world in which the rest of us live.
It's everywhere. One of the ways we encounter it might describe quite well one thing that might have puzzled some listeners. So if we think about radioactive substances, they're always described as their radioactivity in terms of a concept called half-life, which is the amount of time it takes for half of the substance to decay. So you'll hear people talking about the half-life of uranium or whatever, and hence how long we have to look after nuclear waste for. Well, the reason why we have to talk about it in that slightly strange way is that individual atoms decay randomly. All I can say is that they've got a certain probability of decaying in any given, say, minute. So that means when I want to describe what's going on with the decay of that substance, I need to say that the rate of change of the amount of the substance as it decays is proportional to how much of it there is. In fact, it's negatively proportional to how much of it there is because it's decaying. So when you solve an equation like the rate of change of this is proportional to itself, that means you exactly get an answer out looking like e to the second.
June, back to you. Let's now move to Euler. Can you tell us a little about him before we go into what he did?
Yes, I mean Euler is the mathematician of the 18th century, without doubt. His life spans the 18th century. He was born in 1707, he dies in 1783. And he's probably, and we always say probably because I'm not sure, but he's probably the most prolific mathematician that has ever lived. Because I think right at this moment his collected works reach something like 75 volumes, 25 and they're still publishing, and that's well over 200 years after his death. And there's just not a subject he didn't touch really in mathematics and physics. So we just name any subject, whether it's ballistics, astronomy, number theory, cartography, shipbuilding, algebra. It was just extraordinary, his output. And one of the things is really important about him is that he published, and he published like mad. And before him, people like Newton, for example, is well known for being very secretive about his work and not publishing. For Euler, publishing was really, he wanted to get it out there, and he published in different languages. He also corresponded with lots of people, and his correspondence, we've got something like 3,000 letters in the Euler correspondence. Some of the letters are written, he changes language in the middle of the letters. I mean, he was just phenomenal had a phenomenal memory. I mean, there's just so much about him.
He spent all of his time as the court mathematician in Russia.
Yes, he did. He started off
13 children.
He did,
and he had blind halfway through his life, and his children helped him to get on with the job.
Yeah, and he had 2 wives. His house burnt down at some point, and he spent his first bit of his working life in St. Petersburg. Then he goes to Berlin. Then he goes back to St. Petersburg, and of the things that he wrote, apart from all the masses of mathematical papers, there are a number of books, and one of them is particularly important in the context of E, and that's the text that he wrote in 1748.
Just to share that, how did he investigate the property?
He did all sorts of things, and as June mentioned, some of his work was really very practical, kind of dealing with very specific real-world problems that were there. Some of it was playing around with mathematics for the sake of playing around with mathematics, and my sort of hunch is that that's a rather artificial distinction, that he thought he was just investigating interesting things. So he was working in this period just after people were really kind of understanding what calculus was all about, starting to explore things like infinite series. So adding together infinitely many things. So if I've got 10 things on my piece of paper, I can add them together. That might take me a while if I'm not very good at addition, but it's going to be a manageable thing. If I've got infinitely many things I want to add together, that's a more daunting prospect. And it's also quite a subtle prospect, because I have to be very careful to make sure that I understand what kind of answer I'm going to get out at the end. And sometimes when you add together infinitely many things, it doesn't converge. You sort of get something that doesn't behave in a meaningful way. Sometimes you get a nice sensible answer. So one of the things that Euler did was play around with these infinite series relating to e and to the exponential function. So the exponential function is this function e to the x that Culver has talked about already. So very closely bound up with properties with e. So it turns out, for example, that you can write e as an infinite series. So you can write this decimal that we sort of find slightly hard, and it's 2.7 something, and I can never remember what comes after the 7 because it's kind of complicated and unpredictable. But there's this beautiful series, this sum of infinitely many things I can add together to get e, and it's beautiful because it's very predictable. So it's 1 plus 1 over 1 plus 1 over 2 plus 1 over 6 plus 1 over 24 and so on. And the denominators there, the numbers on the bottom of those fractions, form a very nice series, it's very sequence, it's very easy to write down. So Euler played around with a number of things related to this, just kind of testing out, what can I find here? So